Welcome everyone today to the uh, March, what is it, March 3rd edition of our weekly imaging science seminar. And we're just pleased to have Ignacio Zuleta here, and I'll introduce him in a second. I should first say my name is John Caracas. For those who may not know me, I'm one of the professors here at the center. And I had the pleasure of meeting Ignacio a number of different ways, mostly I think at Landsat science team meetings, but also some other workshops and conferences. And I've always been impressed by his clarity of thought and visionary thinking. And I think that's echoed in the title here, Image Formation. I think that's Earth Observation Practicalities at the Speed of Light.
Mm.
Kind of an intriguing title, and we're looking forward to hearing more about that. But let me just say a few words about Ignacio before we get started. He's a native of Argentina, where he received his BS and MS in chemistry, and then he received his doctorate degree from Stanford University in physical chemistry. And after that, he served as a postdoc fellow at the University of California, San Francisco. And I've always liked his little tagline on LinkedIn, space photography for the masses. And maybe he can explain a little bit more about that. But for about 6 years, until very recently, he was the lead manager for payload observations as part of the Planet Labs or Planet satellite system. And I think he'll be explaining more about that, but that's been an exciting development in Earth observation with the couple hundred satellites or more that are out in space. So with that, I'll let Ignacio get started, and we welcome you. We would applaud if we were all in person to invite you to get started, but thank you. Go ahead.
Thank you so much, John. It's a pleasure to be here. I'm very excited to connect with the Rochester community. It's one of the, it's a place that has a very near, it's very near to my heart because we used to source most of our, in my last job, most of our sensors from Rochester. There were CCDs made in the old Kodak factory back there. So I can say we probably exhausted all the sensors we could buy from that town, and we put them in space. So I'm going to walk you a little bit through a little bit of a, personal perspective through my journey, a little bit of my career and, my journey through Planet and some of the things we did. And then a couple of thoughts, I guess I want to say advice about, what to do next and what to think about when you're starting, your career, when you're going to school and, the things that might matter. So maybe for some of you will be interesting enough to steer some of your decisions and interests. So I'll say a little bit of things about my professional path. I think that's always interesting to people, how you get to where you are. I'm a chemist by training. I am not an aerospace engineer. I'll walk you guys through the things that were inspiring to me when I started working in remote sensing and shaped some of the design work I did at Planet, and how we form our team around certain values and vision on the engineering side, and the what engineering problem we tackled, right? And then I'll leave you a couple of words of advice on how to navigate your years in school, and based on the things I enjoyed. I'm a little bit of a perpetual student. I really miss being in school and learning things. These are words of envy. So some of the things I will be doing if I will be back in that state. So my background was really pretty well summarized there by you, John. I was born in Argentina to parents that were, humanities professors. So I've always been, talking to myself and, reading the classics and really reflecting about how the work we do fits, in the big picture of the universe. But I did rebel and become a scientist. So one of the first scientists in my family. And I was very passionate about photography from very early on. So still was also fascinated by what people call the central science of chemistry, right? So it was the science that really connected me all the way from physics to biology, and I spent a long time trying to figure out what it is that I was curious about, and that meandering path took me to where I am right now. So I spent a lot of time doing spectroscopy and instrumentation in my first job. And then when I went to grad school, I spent a lot of time trying to understand how to monitor dynamical systems in the chemical sense. So lots of time doing mass spectrometry, building detectors, time in the clean room, building sensors, ion optics, microfluidics, and then putting everything together, all the mechatronics, like how do you wire things up, interface it, and then putting an optics bench so you can start, shining a laser at a chemical reaction and then sucking all that into vacuum and then doing some ion propagation and modulation and measure maybe the mass of the molecules. So, and simulating everything, right? So that's a lot of what I did in grad school. And then I became very passionate about systems and dynamics, and there's nothing really as interesting in terms of dynamical systems as the systems inside cells. So I tried to combine what I learned into, studying systems inside cells. So I did a lot of single cell imaging with microscopes and, laser induced fluorescence. I learned a lot of genetics in my postdoc, and then went back to something that I really love, which is just to do model simulations to steer experimental design, and then collect data using automated fermentations of yeast, and then figure out what can we learn about, how control theory plays inside cells. So totally different from what I ended up doing in my last job. Right about the time I was deciding what to do next, a job landed on my lap to go take photography to where it had never been taken before, essentially, right? So I ended up connecting my lab for systems and photography and into going into Planet Labs, which was a startup that was just starting at the time. And there I learned a lot about operating measurements at scale, right? So a lot of operations research, sensors, cameras, telescopes. And the one thing I learned is also about people, how I just wanted to do things that require really working with other people, things I couldn't do by myself, and how to really articulate, the design problems across teams and across the company and across the industry. And now I find myself taking a little bit of a breath and thinking about learning about new things. So optical designs, sensor fusion, virtual instruments, I don't know what comes next. So I'm very excited to take this break and be here talking to you guys. So let's talk a little bit about the last problem I was working on. I was working on a problem that is the problem of monitoring the Earth system, right? And the Earth is a very complex system. There's a very simple way to monitor it over time, which is to take pictures of the Earth over time, right? So most of the change in the Earth happens without having a record of it. And the question is, how do we leave a record for future generations of the changes that are happening on the surface of the Earth, right? So we need to monitor our planet continuously using our best technology in a way that the data is going to be usable for future generations. That's at least what motivated me to work on this problem. Of course, we can drive tactical decisions for businesses, for agriculture, environmental monitoring, disaster response, and so on. And a lot of the inspiration came from our predecessors, which is the guys who first put cameras in space to start creating the first temporal records of what was happening on the Earth for the last 20, 30 years, right? So some of the missions that were very inspiring for me were, of course, the Landsat mission, the Sentinel mission, Rapid Eye, MODIS, and Spot 5. So I'm just going to walk you through some pictures to give some of you who might not be familiar with satellites a sense of what are we talking about. So what we're talking about is these things, right? These are what people call satellites. It's a spacecraft, and usually it has several parts in it. There's going to be a big part of that volume that is taken up by a camera that takes pictures. And then there's going to be solar panels to power all that. And then there's going to be all sorts of, power electronics and things like that. It's essentially a camera, like a GoPro flying in space. It's like a drone in space. It's very fascinating. These things have been flying for many years, and they have helped us create our best record of climate change over the last 30 years on the surface of the Earth, right? So it's really exciting. And the way this works is you put these devices in a rocket and you launch them into orbit. And then usually they are attached to some sort of propulsive device where once they get to the required altitude, they get accelerated into the speed of the orbit. Now you end up with a camera that essentially floats in space and circles around the Earth. And then you can take pictures, right? So the more cameras you fly, the more often the pictures you can take. And the more sophisticated your cameras, the more resolution you can have. So it means you can see smaller and smaller objects. So there's many of these kinds of satellites flying around. This is another satellite called Sentinel II. It's flown by the European Space Agency. And it was very interesting because it's one of the first sats where we increased the resolution of the systems. Landsat was originally a 30-meter system. This is more like a 10-meter resolution system. So the idea is we were starting to launch these big systems. They're expensive. They cost about $1 billion each probably to launch end to end and operate. And they will only produce data, every week or every 2 weeks, right? So one of the interesting problems that we were starting to realize that was an opportunity was like, how do we create these missions? How do we realize them for cheaper? How do we create higher resolution imagery? How do we get imagery more often, right? And the inspiration was always how to complement and strengthen the role that these Pathfinders missions have had, right? This is another mission called Rapid Eye. That was one of the first missions where you could get an image of any point in the Earth or any given day, but not everywhere simultaneously. It was a very high resolution mission too. It was a 5-meter resolution instrument. There's another mission called MODIS, which is a radiometer, and it's a wide field of view, very radiometrically accurate instrument that flies on a synchronous orbit. So the idea is we had all these instruments floating around, but there was no single mission that would collect high resolution imagery every single day and over the entire Earth, right? So that started shaping a little bit of a problem, right? And this is this is a reference mission. The most beautiful of them all is the Landsat mission, of which we just launched did we launch it? I don't remember. It was Landsat 8. This is a picture of Landsat 8, and there's a follow-on mission called Landsat 9, which is another instrument just like this. And this has been kind of the gold standard for Earth observation, creating essentially calibratable records of the Earth's surface over the last 20 years in this program. So it's been really exciting. It was very inspiring. And what we started to figure out when I came to Planet is we needed to decide in what direction we took the company, right? And I did a lot of work pushing externally, internally, for making sure that what we did build in Planet was a way to revisit and monitor the Earth every single day that was interoperable with the record that these missions were creating, right? So we could start complementing that record and leaving a record of data that could be used in conjunction with the Landsat record to understand in the future what happened. How did we get here, right? So a lot of you might not be familiar with satellites. I figured I would show a small satellite so I could walk you a little bit through the parts in a satellite. The satellites are very simple. Usually you have a telescope in the front, and then in the middle, you're going to have a camera system, which usually is going to be a CMOS or a CCD sensor. And then there's going to be a bunch of electronics on the back. Usually it's going to be batteries, accelerometers, gyroscopes, anything that helps you understand where the satellite is pointing, right? So a lot of my work over the last 6.5 years was developing the front 2/3 of the system, right? The camera and the telescopes, and understanding how we could walk ourselves from a design that was very inexpensive and not calibratable to a design that produced data that was interoperable with the data from the public missions. This is how a real payload looks like, right? This is like a real satellite in the lab. This is a picture of Landsat. Now you can see that what we're trying to understand is, could we build a version of this beautiful instrument that complements this class of instruments, providing higher resolution data every day? So you put these things in space, and now you can start monitoring the Earth. What is the data you get out of this? Well, it's going to look like on the left, you're going to have a picture you take from a drone or from an airplane. And on the right, you're going to see the pictures you take from satellites, right? So just to recalibrate how you think about imaging systems, these images have been historically low resolution, right? And this is an example of Landsat versus an aerial image, and gives you a sense of how coarse the resolution of the system is, right? Now, when you put it together, the power is not in the resolution, it's the ability to massively image the Earth at the continental scale. You can start putting together these massive composites that tell you what's going on at the continental scale, right? And this is the power of monitoring Earth observation, right? Is create movies and maps of the Earth that helps us track at the global scale what's going on Earth, and understanding global trends, right? And this is in opposition to high resolution systems. That's a beautiful vision, but at the end of the day, you have to translate it to a technical problem, right? So what we're trying to really do here is we're trying to achieve a daily revisit time. And that means we have to build, for the class of satellites we're looking at, missions that are between 80 and 150 satellites, right? It's very hard, right? These are the biggest Earth observation missions ever launched. During my time at Planet, our group launched probably about 300 satellites. So it's a big number of satellites. And we also wanted to have high resolution. So that's why I was, actually one of the pictures earlier was of Spot 5, which is another sat. I got them confused. We wanted to have a resolution that was what we call the Spot 5 resolution regime, which is between 3 and 5 meters of resolution to enable a lot of new applications in agriculture and environmental monitoring. That dictated that we needed telescopes that were about 10 centimeters in diameter, right? We also wanted the data to be interoperable with Landsat and Sentinel spectral bands. And we wanted to craft a product that was globally seamless, right? So we needed to approach calibration with a sensor fusion approach, right? So not the traditional, regress the data to align and fit, but instead trying to pull all the data and create the maximum likelihood picture of what was going on the Earth, right? Which is a completely different approach. So this is a year that was going to take us, this is a problem that was going to take us many years to solve. So we just got started and started working on it many years ago. We iterated through the satellites many times. This is just, of course, a subset of hardware iterations, but this is how the satellites look like. You can see that over time, there's been like minute changes to how the satellites were constructed, what kind of antennas they had, solar panels, number of solar panels, and so on. So you can see here the telescope. There's a flap with all the communication equipment. And then you have solar panels that are facing down here. And then on the back, you're going to have a lot of optical navigation equipment like star trackers, horizon sensors, sun sensors, and so on. Just to give you a sense of the size, this is a picture we used a lot in the early days, just to really, show, what are we talking about here, right? We're talking about missions that are like the size of a bus, literally, with satellites that are the size of a shoebox, right? So the idea here is what we call a disaggregated constellation, right? We're taking a single mission that was used to employ a single satellite with a very wide field of view and infrequent observations. And then we're disaggregating that field of view over an orbit, essentially, and forming a ring of satellites that now continuously revisit every point on the Earth once a day, right, at higher resolution. So for those of you who are into how these systems work, a lot of the innovation happened on the camera and the focal plane. We had when you have a payload, there is two parts to a payload. You have what people call the foreoptic or the telescope, and then you have the camera and the focal plane. And a lot of the action came from iterating the cameras really fast, usually twice as fast as the telescopes in practice, right? So we designed probably 3 telescopes over the time I was there, and well, maybe 4, but about 3. And then we iterated the cameras a lot of times. So these are 4 of the iterations that actually ended up turning into products. And these are really interesting for anyone who is geeking out about sensors and layouts and how you build a picture in space. So these are all charge coupled devices, right? They're all CCDs. They were all made in Rochester. They were made in the old onsemi factory that closed about a year ago now. And they were of different sizes. And they were very exciting because one of the things these sensors afforded us is to implement in the sensor motion compensation, because these are systems that are very small. And every time you miniaturized an optical system, an imaging system, the first thing you're going to miniaturize is the light throughput, because the area of your pupil is going to shrink, right? So one of the first problems we needed to solve is how to implement motion compensation on the sensor, right? So these charge coupled devices have been used on interplanetary missions, And because of the way they're constructed, you can repurpose the structures on the sensors that constitute the global shutter, the electronic shutter, to move the charge on the sensor at the speed the objects move on the ground. So that gives you motion compensation, which means you can integrate for longer times than the one that is dictated by the size of a pixel. So that's a detail and a little aside. Now, our first sensors were Bayer patterns, right? They were essentially normal RGB sensors, and you can see a picture in our pilot here where, you know, we got essentially an image that needed to be debayered, and all we need to do is to interpolate up the images and to create a color composite, essentially. Now, that system had a lot of advantages and disadvantages, right? One of the disadvantages was that you were losing spatial resolution due to undersampling. The other disadvantage was that spectrally, these pixels were defined using color dyes. So they have very broad spectral responses that you see in this plot here, right? Right. So, and this meant that this data was not readily interoperable with the public missions, right? It had a different color space, if you want to think about it, right? And it was not really cross-calibratable to the public missions. The second iteration for us involved adding a near-infrared bandpass filter on one half of the sensor. So that helped us create the first version of the sensor that could look at vegetation health, right? The response in the near-infrared is very important for vegetation health. And you can see here, we added this spectral band in 2017. That mission of 150 satellites was, at the time we launched it, the largest satellite constellation ever launched, period. It was, of course, the biggest Earth observation constellation. And it was the first time anyone monitored the Earth with a daily cadence every single day at a sampling resolution of 3 meters. So that was a big breakthrough. And there was, of course, a lot of challenges in that data, right? It was not readily calibratable because of the reasons I was just discussing. And of course, building 150 telescopes that are sharp is a challenge. So we struggled a lot also trying to figure out, how do we manufacture at scale a device that everybody else manufactures one at a time, right? So the direction of our development took us to derive a new version of the instrument, which we call the DAB Refresh, where we started prioritizing adding spectral bands, colors in the sensor that were interoperable with the public mission that we picked at the time, the Sentinel II mission. So we came up with a lot of optical technology and coatings to produce very high quality filters that had very precise transmission bands, right? What is the meaning of that practically? It meant that when you overlaid an image from a public mission, for example, Sentinel II, which is a public mission run by ESA that is equivalent to Landsat, with one of these DAB refresh satellites, the data was virtually indistinguishable to statistical error, right? And this was really important because it meant that you could repurpose all the literature from those public missions and apply it to this new data at a higher revisit rate and a higher resolution. You did not have to reinvent how you interpreted the data, because a lot of that variability did come from the spectral responses, right? And then the last design we worked on was what we call the Super DAB, which was 8 spectral bands, where we covered a lot of the spectral bands from Sentinel II that were not in the infrared, in the shortwave infrared. And then we added some new bands that other systems didn't have. And as you can see, this is achieved by overlaying filters on top of a CCD, and then using photogrammetry to realign these slivers of data on top of each other to produce a composite, right? So every little step here was the work of many people, right? And it was, of course, painful at the beginning, right? So none of these things had ever been done before when we did them. So how did the actual images look like, right? And these are examples from the super early designs, right? You can get a sense, right? We flew telescopes that had a lot of vignetting. So the images were, well, we thought they were beautiful, but they were not very scientifically usable. And we did a lot of algorithm development to understand what was the focus of the images. So you can see a little, we used to do automatic reconstruction of the actual kernel that represented the optical system, the point spread function. And, we went through all the different designs, right? And here you get a sense of when we took this raw data to create these composites, what we needed to do is a process called orthorectification, which is we tie down the imagery to a reference image to produce our color composites. In the later designs, we ended up building what's called essentially a structure from motion pipeline, where the relative motion of the camera between different frames, subframes, is reconstructed and used to produce the color composites. This is an example here where you can see another composite from the SuperDAT design. So the other thing that was very exciting is we started getting better at predicting and understanding the optical performance of the system. This is, from a presentation in Calcon from our optical lead when I was back in the team, where we started essentially predicting, the resolution of the system in the lab, and then matching that with resolution measurements that were done in the ground, which was a big breakthrough, right? Because these are systems that are extremely high performance, they're diffraction limited, edge-to-edge type of optical systems in a very small envelope. So they're really, really hard to manufacture and operate in space. So what we did conceptually is we combined essentially the best of missions that existed, and we proposed an architecture where we disaggregated the existing missions into many, many small little sats, right? So what we did is we took the resolution of a sat like Spot 5, we took the spectral bands of Sentinel, and we created a system where every picture you take is taken with essentially with a longer focal length lens compared to the bigger missions, because the bigger missions cover a lot of terrain by using very fast lenses. What that meant is that the image of a tall object on the edge of a field of view look different than if it's in the center of the field of view. You will get what's called lean, right? So we created a system where all the pictures that are created are essentially interchangeable between different points on Earth, which is not the case for the big systems. So it's what people call orthophotos. Daily revisit, the full field of view of the instrument was calibratable, a very low stray light, and we increased a lot what's called the quantum efficiency of the sensor in the near infrared. So we combined all these missions and created what we believe was a virtual instrument that was implemented using a constellation of satellites that was better than the sum of the parts. And again, that virtual constellation concept had never been proposed before, but it had never been realized. So all these systems have different spectral bands, and this is a plot where you can see, atmospheric transmission in the gray area here. These are areas where, if you look from space, the atmosphere is going to be absorbing a lot of different bands. And in general, if you want to look at the surface of the Earth, you're going to have your system transmit colors that are in the areas where you get high atmospheric transmission, right? So you can see these little boxes are going to be the spectral bands of different missions, as an example, right? You have Sentinel II and Landsat 7 and 8. So what we did is we built a system that had bands that were interoperable between Sentinel and the SuperDAP, right? So you can see in this plot, essentially in the solid lines are going to be the SuperDAP lab measured transmission bands. And then in the dotted lines, these are the Sentinel transmissions, right? So we created a system that had the same spectral bands. Moreover, we measured all this data for every single sat, and we manufacture these sats, by the hundreds. And so we characterize our instruments individually, probably better than the big instruments in the sense of the detail of the data we collected. So then when you look at an image that has very high contrast, right? Like for example, these glaciers in Antarctica, what you can see is across the full dynamic range of reflectances that you can see from space, the data between Sentinel II and this SuperDAP design corresponds to each other. right? That means the data is interoperable. So, and when you look at a time series, you can see in this time, this is a time series when you look at a single spot on the Earth, you're gonna see data from different versions of satellites in different colors. And in green, you're gonna have some of the older, essentially, designs from the DABs, which didn't give you data that interoperated or reproduce Sentinel and Landsat. So you have the blue dots here are gonna be Landsat 8. And then you're gonna have Sentinel II are gonna be the red boxes. And then you see that for the super DAB design, which is the orange boxes, which is the last iteration, we started achieving interoperability with the public missions. And this is out of the level 2 calibration, right? This continuous line was the last project that, was being worked on when I left, which is we created a sensor fusion product that combined all the data into a maximum likelihood representation of what's happening on the Earth at that point in time, right? And it also involves some model-based gap filling for times where you have clouds. And it is what I believe is the future of Earth observation products, right? It's sensor fusion experimental designs where you are processing the data by design, by pulling orthogonal sources of data, right? So this was very exciting, right? Because it took us essentially, we started with a goal, 6.5 years ago, and we essentially went after each of the technical problems that we needed to solve, keeping the telescopes sharp, making them interoperable, increasing the field of view, increasing the number of spectral bands, make them interoperable, to reach this, essentially this goal, which was to create data that was scientifically usable alongside the public data. I don't remember the numbers these days, but by the time I left in October, a peer review paper was being accepted or published every other day on the data from these satellites. So it's very exciting to see that the data was being used, and because it was new data and better in many ways, was being used in many new ways. So these are just some examples. I literally pulled this out of the webpage because these are from the last batch that was launched after I left, and beautiful imagery. You have to remember the functionality here of the system. This is a system that is 35 kilometers field of view at 500 kilometers of altitude, where there is probably 30 single subframes that go into the single color frame you see here, right, to reconstruct this together. So there is very sophisticated, photogrammetry. This is one of the hardest problems to solve. Just in putting the image together to make this example I have here for you. And the entire satellite is the size of a shoebox. So 10 of these satellites have the field of view of Sentinel, essentially, for a tiny fraction of the complexity. So more examples. And then, so, what were the challenges in retrospective? Some of the challenges are like anytime you get a more precise process or tool, right? When you make many of anything, you get variance. And one of the things we discovered was that it was very hard to calibrate if we were doing things right or wrong, because we were comparing ourselves to systems that had only been realized once, right? So we didn't understand if the variance we were seeing in the data or in the manufacturing or in the testing was too big or too small, but it was never zero, right? So we struggled a lot trying to calibrate essentially what was good enough, right? The other big challenge was motion compensation, and I think we decisively solved it for the technology we had available at the time, right? So when you size a system down, the first thing you run out of is light, right? A big reason the big telescopes were big is because they didn't have motion compensation and they needed to harvest light. They were not big because of image resolution concerns. So those were the things that were pretty hard. And then there was a lot of leftover problems that we ran into hard walls that were really interesting, but they were clearly for the future, which I think, are kind of the things to invest on in terms of, I guess, training or research or, if anything, interest and creativity, right? So what's hot, right, in terms of the enablers that are going to be needed for Earth observation? I think a big one is always going to be motion compensation techniques. That's always going to be an area that is going to open up a miniaturization of systems and flexibility of operation of space payloads. Sensor fusion, I think we have a very rich literature right now coming from the self-driving car industry. So the math is laid out. The photogrammetry has been developed to a level that it was not there 5 years ago. So there's a beautiful, rich greenfield opportunity to put sensor fusion to work in space in many different ways. The other one is most systems are over-engineered, they're oversampled. So understanding the math and the algorithmics and the limitations of image restoration and image reconstruction and super resolution, it's fundamental, because one of the biggest drivers of the cost of space systems is the desired resolution, right? But it's very likely a lot of systems are over-engineered. Thermal imaging is another big challenge. Short and mid-wave infrared imaging is another big challenge. What do I mean by that? It's hard to do it cheap, right? Compression algorithms, right? We're compressing images for most applications in space and other applications with algorithms that were designed to take pictures of cats, right? So it's an entire greenfield opportunity to think deeply about how do we compress images, right? And how do we compress them in a way that is friendly to exploitation? And the last one that is always, the holy grail of a lot of these applications is deployable optics, right? How do we make compressed compact systems, optical systems that deploy to the final size when you use them on the ground, in space, on airplanes, on drones, whatever. The size of the system matters actually for performance. So anyhow, those are my thoughts in terms of the technology. I think, given that you guys are in school and trying to reflect about what to do next and your education, I just put a couple of slides that are, feel free to ignore them. They're just I was thinking aloud about what would I tell myself if I needed to decide next steps. Something I think a lot about is about abstract skills and practical knowledge, right? And I think one of the things I struggle with, when I was in school was balancing the temptation to jump into practical applications and apply courses, project courses and sciences versus abstraction. And the way I think about it is how you tackle acting on things and ideas, right? And I think I really, every time somebody asks me about what to focus on, I always say, focus on the things that are harder to focus on. You have to delay gratification, right? And what's hard to focus on? The things that are abstract. Now, they are the ones you're going to use forever, right? So I always, when I have people in my team that I was mentoring or students, I always say, there's some things, if you're in the imaging business, that it always pays off to have deep knowledge on, and it's timeless, right? And those are going to be, advanced linear algebra, differential equations, signal processing, know your Fourier transforms in 1D and 2D inside out, probability. For those of you on the sensor side, I think on the payloads, a topic that is underappreciated is statistical mechanics, physical optics, and EM. And then for those of you just who want to put things in perspective, it's just knowing about the scientific method in a deep sense, right? The history of science, how things have been developed, where things come from. Because it's very likely you're going to be transiting those paths again, right? And then the practical stuff is important. It has to be weaved in, but it can be left a little bit for later. These are the things that help you prototype ideas as opposed to decide if something is a good idea or not, right? So software engineering, computer architecture, lab electronics, lab physics, mechatronics. If you're into sensors, well, knowing about MEMS and how to, find your way around the clean room, how to characterize films, those are good technical skills to know, and you're going to use them, but they will change over time. They'll become stale. New things will come and replace them and obsolete them. So you have to be very careful about not over-investing yourself in some of these, because you'll learn them on the job. So what matters? I love learning, so I'm giving this piece of advice just thinking about learning in life, right? So you'll never know when life is going to take you. I started as a chemist. I've done biology. I ended up helping build satellite systems. And we all learn very different ways, right? You do learn by doing, and you also learn by thinking and dreaming. You have to abstract things away. And thinking and dreaming actually is harder. It's more of a learned skill because it requires focusing on what things can be, right? And this is really important because it's what helps you decide what's worth the effort, right? And what's worth your time, which is the only thing you don't have infinite of, right? So the applied skills are very, very learned on the job, I think, and not in school, in my opinion. So it's super important to load up on a healthy load of thinking and abstract thinking early on, because those skills you'll use forever. And then, but still, the practical skills and the abstract skills, you will forget them and you will relearn them many times over, right? So still, nothing is really ever under our belt completely, right? Most of the things we don't know that we don't know them. So, still you have to be patient with yourself, right? And not get stressed out about the things you don't know. So anyhow, I don't know if this makes any sense. I want to stop here for some questions. And back to you, John, for guidance on how you want to use this, if we have a few more minutes.
Yeah, we got about 15 minutes in the hour left, but thank you very much. I applaud for that. And it's just a very interesting walk through your background, your career, and how you managed, along with your team, to create this very interesting daily observations. And so I have some questions, but we'll certainly open it up, particularly if some of the students have some questions. I'd like to follow up on any of the topics. You feel free to put it in the chat or unmute yourself. I think all the folks that are connected have that ability, and Ignacio would be happy to respond to any questions.
I don't know if I can see the chat, so you might have to read the questions for me, John.
I will. I can do that. Sure.
Hi, I have a question.
Yes, please go ahead, Chase.
Yeah, I'm wondering, it really seems like, calibrating a constellation of these CubeSats is kind of a difficult problem, because, each one has their own, characteristics and gains and stuff. Is there an ongoing effort to mitigate, or I guess improve, the accuracy? Are you guys kind of relying on vicarious calibration and looking at targets on the ground and those sort of methods?
Yeah, that's a really good question. When I talk about calibration, I want to be very clear that it's a multidimensional problem, right? When I was in my group, there was a full group of 5 people just doing that. So it's a thing. Now, how do you do it? It starts on the ground, right? Now, the question that is important, in my opinion, when you build a distributed system is not how you calibrate it, is if it is calibratable, right? And under what regimes of operation is calibratable? What are the temperatures? What are the ranges of brightness and so on? So that all starts on the ground and it can be verified on orbit. So you have precision and accuracy, right? At the end of the day, you want to understand, does there exist a calibration curve, right? For if the system is not performant, maybe the calibration changes with different temperatures and so on. What we found in practice is that the systems could be calibrated by exploiting massive data sets of near simultaneous overpasses with themselves or public missions, right? So let me put it that way. You took a picture of an object, you were flying right underneath Landsat, you did a regression for that satellite, you did the same thing for another satellite, you took a picture of third day, overlay the images, and they look the same, right? So calibration at the end of the day kind of worked. I mean, we needed to eliminate the sources of lack of calibratability. And in our system were a couple, were temperature, for example. So you end up loading lookup tables to the satellite. So you know essentially the temperature of the sensor, and you can either do adjustments or you do the adjustment on the ground. When the satellite leaves And eclipse and stars imaging is colder, and by the time it reaches the equator is warmer. That is a different, that already, and you measure those temperatures. That's calibratable. Then there is non-calibratable sources. Classic example, stray light. The early generations of satellites suffer from stray light. Depending on what you were looking at, there was a floating offset on that regression. Very hard problem to do, right? And so that requires sensor fusion approaches, where we leveraged pulling a lot of lower resolution data that was near simultaneous to pin down the y-intercept, but conserve the spatial resolution and the linearity and the dynamic range. So we did a lot of poor man's sensor fusion. Now that sensor fusion is mainstream, inference, maximum likelihood, or Kalman filters, all that stuff is more mainstream. Now we have a framework to think about that. But back in the early days, when the team came from different disciplines, more traditional Calval, all we could do is turn the problem into some sort of sophisticated regression. What is the limit? What comes next in terms of calibration tech? Onboard radiation sources, right? Onboard calibrators. This is something we never implemented, and the big sats have that. And that's important for the ultimate long-term stability, right? Monitoring of the system. But those things also break, as we know from the big satellites too. So we don't know if we could do that 150 times over and get it right every time, right? So we always lean on transferring the calibration from bigger sats to disaggregated constellations, just to wrap up the answer, right? It's a tiered calibration scheme. That's the right way to do it. You have a reference instrument and you transfer the calibration to the distributed constellation. That's the most efficient way to do it. And the new architectures that are coming up for Landsat Next and other missions that are being designed, Sentinel II, next generation, and so on, will be probably tiered. There will be a calibration source flying on top of sats that inherit that calibration via calibration transfer. Does that answer your question?
Yeah, it does. Thank you.
Great, thank you. Another question from our audience?
I had a couple of questions. Are you flying like constellation, like essentially in a big line parallel to each other?
We're having a really hard time understanding you. I'm sorry, we can't understand the audio. Perhaps you can put it in the chat, or not sure what happened there. Any other questions? Okay, I see it. So Austin says, I was curious about the formation of the constellation. So perhaps the orbital dynamics.
Yeah. I can tell you a couple of things about that. The constellation is designed to, let me see, how can we do this? There's so many ways, levels of explanation, right? The way to think about it conceptually is, let me see, how do we say this?
And he followed up with asking, are they all fly in parallel planes?
No. They're all in a single orbital plane. Essentially, what you do is you launch into that orbital plane. They're all clamped together. And then what you're going to use is you're going to exploit a very small amount of drag in the atmosphere by orienting the solar panels in different orientations to spread in a string of pearls type of configuration in that one orbital plane all the satellites to the point they're equally spaced. And what you have is just enough satellites so the actual swath widths of the sats overlay essentially on the perimeter of the Earth, right? So, and you can do that calculation, right? And so within the span of a day, in the morning, you're going to be hitting essentially every point in the Earth. So single orbital plane, these are called sun-synchronous orbits. It means that essentially it's going to be the same solar time every time you cross a place in the Earth, and they're polar orbits, right? As opposed to high incline orbits. So what is the meaning of that? The sat always flies at the same solar time over a given spot on the Earth. This is different from orbits like we use for the communication satellites or other high revisit constellations or the ISS, right? The ISS crosses every point on the Earth at a different time of the day, right? So that data is not really interoperable because you will be mixing pictures of the afternoon with the morning and the night and so on. So it's a polar orbit, sun-synchronous, single plane, equally spaced. And I think you can probably Google the rest.
Great, thank you. Well, I'll ask a question while folks may be thinking, and this is more of an open-ended general question. I'm curious about your thoughts about the emergence or the direction of moving toward open science and all the implications of that. You've worked in academia, you have a research perspective, you come from an academic family where openness is valued. You also worked in a private company where IP and other things is how you make money. So is there a path forward to balance this? Because we're seeing more and more pressure from funding agencies to publish in open access journals, make our data available to anyone, make our code available to anyone. I'm sure you have many thoughts about that, but maybe just a couple minutes to give a perspective.
Yeah, I mean, I would say that both academia and industry are both open and closed in certain ways, right? So I was very fortunate that Planet gave me a lot of autonomy to do public speaking and try to share a lot of the work we did as much as we did, way more than our competitors, but it's still, a little bit closed, especially when you talk about strategy and so on. But we did try to contribute to, scientific endeavors by giving data away. Now, we could not talk about how we did things, and that created a challenge to open science. Why? Because the data was not fully traceable, right? If I cannot give you a source code and tell you what sensor I'm using and publish a paper about it, ultimately, if you're going to write a paper about that data, you have a breakdown in traceability. There's no way around it. So now, what has happened with interactions when I was in academia, and I've seen it when I was in industry? Academia is open. Everybody has to. I was working in biology for a while, which is very open. Like when you publish, you need to dump the raw data sets. You need to put the code. Great. What happens? That's preceded by long embargoes because people are trying to milk the data. Why? Because the data is money to them too, right? So I've been in many situations where I interact with academia and they say, okay, we're going to open source it. And then they open source it years later or after the fact. Whereas in my mind, open source and open data means being open about what you're doing as you're doing it, right? An open source project is a project where the code is from the first pull request in the open and anyone can contribute. You take input from others. It's not a dump of code in the open where you cannot change it, it's too late, and so on. So neither schemes are perfect, and we don't have a model of how to do open technology, I would say, in general. That's one of the challenges. Now, do the models exist? Of course, they do exist. If you look at how cell phones are developed, like the code base of Android, it's an open source thing. Chrome, your browser, is open source. Like there is Mozilla Foundation. All that data is paid by all the companies, and they all get royalty-free access to the same pool of technology. All the IP that is done so cell phones interact with each other, right? All that RF technology is all interoperable, otherwise phones wouldn't work, right? So there is IP pools with free cross-licensing for everybody. Microprocessors, right? You execute your computer program in AMD, Intel, they all cross-license the tech, otherwise things don't run, and they're competitors, right? Semiconductor processes, the same thing. Otherwise you wouldn't be able to move a process from one fab to another. So you can have openness, you can have profitability at the academic or private level, but you can't do away with opaqueness. What you need is a mechanism to enforce or articulate camaraderie in the industry, so you can have advanced, so we can solve the problems that are truly new. Because the situation we have right now, and a lot of science happens too, and happens in the private sector, is we're all repeating the solutions to the problems because We know we're reinventing the wheel, but we don't want to help the other guy reinvent the wheel. But then we're all reinventing the wheel. So we cannot establish in a clear fashion where is the state of the art, what is truly new and innovative. So then, as a society, we waste money, right? Because we reinvent the same thing many times over. So I think we need a traceability end to end, and it's going to become, and it's going to be driven, like always, by money, right? And I've seen that example to talk about an Earth systems problem, right? Carbon credits, right? If I'm going to be buying and selling carbon credits, I'm going to need a way to verify, and the way to verify has to be traceable, not because we're nice. It has to be traceable because the customers of that, the guys who write the check, the guys who receive it, who are insurance companies, hedge funds, manufacturers, whatever, countries, they will want to know. It will have to be in the open. So all that technology in Earth observation, sensors, algorithms, analytics, it has to be open. Why? Because it's about money, right? So the very reasons that make it closed sometimes make it open. You need the right incentives. How do we do that with science? I don't know. We need to depart science from credentialing, which is competing on who gets more papers, because then it's a race to the bottom, and start encouraging more collective teamwork that you see in some disciplines, right? When you look at a paper from somebody who works in a linear accelerator, there's like 3 generations of engineers trying to build an ion lens or something, or a detector, right? There's like 50 authors in the papers. Let's talk about teams. Let's talk about and let's acknowledge the fact that there is too much demand and oversupply for certain jobs, to become a professor, to have grants, and build mechanisms for people to do R&D and make a living in industry without feeling, oh, they left science, they feel they failed or something because they're not doing R&D. Well, guess what? I was in Planet not doing R&D, and actually it was all R&D. So it's about, we need to talk more and relabel things and relieve the pressure on academia, on credentialing, direct a lot of the graduates to other places where they're going to do exactly the same work by a different name, and then just invite people to be more open. But we need the right incentives, I think. Does that make sense, or I don't know if this is useful?
Absolutely. It's not an easy question, and there's a lot of different dimensions to it.
I know.
So I think we've reached the end of the hour, so I will go ahead and close the seminar. Do you have a few minutes to stick around and chat?
Yeah,
if folks
of course.
Virtually want to come down to the platform, so to speak, and
yeah, I'm not going anywhere. I might need to do a little bio break of a minute, but I'm going to stay online. All I'm going to do is mute my mic. I'll be back.
Great. Thank you very much.
You're most welcome. Thanks for coming.